want to do now is I want to compare the efficiency of a reversible engine and irreversible engine. And I want to use the second law of thermodynamics to show you that if you compare these two engines, one reversible, the other whatever, reversible or not, and they operate between two same temperature reservoirs, T hot and T cold, I want to show you that the reversible engine must have an efficiency that is at least not lower than the other engine. In other words, if you compare two engines, one reversible and the other reversible or not, the reversible engine must have the higher efficiency. At least it's not lower than the other. Okay? Let's see why we can use the second law of thermodynamics to prove that. Let's say we have, what's a reversible engine, by the way? A reversible engine can run backwards. You know, if an engine runs forward, for example, then what it does, it takes some heat, right? Takes some heat in, and it does, part of it is used to do work, another part is dumped to the cold temperature source. That's an engine running forward. A reversible engine can not only do this, but it can also run backwards. In other words, it absorbs some heat from a low temperature source, and somebody inputs some work, and it takes this work plus Q cold and dump it all the way up to the high temperature source. This, in fact, is an engine running backwards. We can think of it as a refrigerator. Okay, here is inside the refrigerator. This is the power supply from the wall outlet. So electrical energy comes in. You pump some heat from inside the refrigerator and dump it to the environment. So that's how you run the engine backwards. Okay, here's the thing. Suppose this is a reversible engine. And what I'm going to do is I'm going to operate backwards. Okay, I'm going to operate backwards. If you want to operate this thing backwards, you need some energy input, right? You need energy input. You know, plug into power supply, whatever. And let me assume that we also have another engine which runs forward. And that engine, of course, produces some work, right? Produce some work. And I'm going to use that work to run the reversible engine backwards. Remember, we need some energy input to run something backwards, right? So that's what I'm going to do. I'm going to take that work and put it in here. Okay? And, of course, you know, as a result, I can pump some energy, pump some heat from a low temperature source to a high temperature source. Okay, now I want to show you, based on this argument, based on this scenario, I want to show you that this reversible engine must have efficiency that is higher, at least not lower than the other engine. To see this, let's look at some numbers, shall we? Let's say, for simplicity, this is a normal engine. I don't know if it's reversible or not. Okay, let's say it takes 100 joules of heat. Okay, and uses 60 joules of that to do work, and the other 40 joules get lost. Okay, so that's 60 joules. And then here you have a reversible engine operating between two same temperatures, which I am now operating backwards. Okay, I'm operating as a refrigerator. Let me assume that this reversible engine has a lower efficiency than the other engine. What I want to show you is that this assumption is not true because it violates the second law of thermodynamics. How do I show that? Well, assuming that this reversible engine has a lower efficiency than the other engine, then if you were to operate this thing forward, not backward, okay, then for it to produce 60 joules of energy, it would have to take in more energy than 100 joules, right? Because that's, you know, we just said its energy efficiency of this guy is lower than that guy. That guy is 60%, right? 60 joules over 100 joules. This one is less than 60%, less than 60%. So in order to output 60 joules, you must take in more energy. In other words, maybe 120 joules, whatever. Okay, let's say it's 120 joules. So if you run it backwards, then for every 60 joules you take out, you got 120 joules dumped to the high temperature source. All right? So that when this thing runs forward, you have, for every 120 joules, you get 60 joules of work output. In other words, its efficiency is 50%. That guy is 60%. I just want to show you that this is not quite possible. Okay, here. What does the first law of thermodynamics tell us about this reversible engine? Okay, somebody puts in 60 joules, you got 120 joules out. Where did the other 60 come from? It must come from the cold temperature source, right? All right, now let me take a look at this whole thing here. I'm going to take a look at this whole thing as a combined machine, okay? As a combined machine. And let's take a look at what this magical machine does to the environment. Okay, I'm going to link them together because after all, they're really the same temperature, right? The same temperature. So after one cycle, what does this wonderful machine in the green magic box achieve? Well, it took 100 joules from high temperature source, but returned 120 joules. So overall, the high temperature source gained what? 20 joules, right? Meanwhile, as far as work is done, okay, it generates 60 joules from this side and use that 60 joules to do something else. So nothing really happened to the engine. The engine just go back to itself. Okay, now what about the low temperature source? The low temperature source got 40 joules, but then somebody took 60 joules out of it, so the low temperature source lost 20 joules. So this is the net effect of this combined engine going this. You take this guy and that guy combined. This magical machine achieved a wonderful effect. You get a refrigerator that costs you no energy. The net effect is that you pumped 20 joules of heat from the cold temperature to the hot temperature, right? This guy lost 20, this guy gained 20. You see, that directly violates something. What it violates? It violated the Clausius statement of the second law of thermodynamics, which says you can never pump heat from low to high temperature without causing any other change in the world. We have just violated that. So what did that tell you? Our assumption was wrong. What was our assumption? Our assumption was that this reversible engine had lower efficiency than this irreversible engine. You see that? Or just any other engine, that is. So that tells us, based on the second law, it tells us the reversible engine, irreversible, must be greater or equal to the efficiency of another engine running between the same two temperatures. All right, this is the first step towards establishing the efficiency, the highest efficiency of an engine running between two temperatures. What's the next step? Here's the next logical step. Now that we know that the reversible engine is at least not worse than any other engine, okay? But what if I have two reversible engines, ER1 and ER2? They run between the same two temperatures, T cold and T hot. On the one hand, we know ER1 has to be greater or equal to ER2, right? Because the reversible engine is at least not worse than any other engine. But on the other hand, ER2, R2 is also, this second engine is also reversible, which means ER2 is also greater or equal to ER1, right? So they're both equal, greater than the other. What's the only way out? Well, they're equal. They must be equal. So what did that tell us? It tells us that if you look at two temperatures, T hot and T cold, you design any reversible engine between them, operating between them, these two reversible engines must have the exact same efficiency. So not only is the reversible engine special because it's got the highest possible efficiency, but all reversible engines operating between two temperatures, two fixed temperatures, must have the same identical efficiency. In other words, it doesn't matter the detailed engineering of how I make that engine, what kind of working agent do I use? Do I use a gas? Do I use a liquid? Whatever I do, okay, as long as the engine operates between the same two temperatures, T hot and T cold, as long as the engine is reversible, the efficiency is the same. It has nothing to do with the details of the construction of the engine. And that is a remarkable result. It came out of almost nowhere. Just the second law of thermodynamics, which is a very, very general statement. But it is telling us that as long as you can construct a reversible engine operating between T hot and T cold, no matter how you construct it, the result for the efficiency will be exactly the same and will be the highest possible. So, for that reason, why don't I take a look at a very simple reversible engine operating between the same two temperatures. I am going to construct what's called a Carnot cycle. This is named after the French physicist and engineer Sadi Carnot, who was born about 300 years ago. So that was necessary during the French Revolution. You want to figure out how do you make a very, very highly efficient engine. Okay, we look at what's called Carnot cycle. So here, the special type of engine we use is made of ideal gas. Okay, it's made of ideal gas, and this ideal gas undergoes a cyclic process like every engine does, right? You have to go through a cycle and then repeat itself, right? This particular cycle is called a Carnot cycle. Every step is reversible. So the Carnot cycle, the Carnot engine is also reversible. A Carnot engine is something that runs in a Carnot cycle. And if I calculate the efficiency of the Carnot cycle, whatever it is, it's got to be the highest possible efficiency. For any engine running between these two temperatures, it must also be the same for all reversible engines running between the same two temperatures. Okay, so what is a Carnot cycle? Well, let's say the ideal gas starts from point A, okay, on the PV diagram, it starts from point A and goes from here to there at a constant temperature, TH. In other words, you let the gas to be in contact with high temperature source as it expands, okay, so you just give it some heat, right? The temperature of the gas remains at T hot, so it expands, okay? It expands to point B, so this is the isothermal line here. All right, at that point, what I'm going to do is I'm allow the gas to continue to expand, but without adding or removing heat from it. So this is adiabatic from B to C. So Q is equal to 0 here. Isothermal, adiabatic. Once it reaches this point, it's got a greater volume but lower temperature. And then what I do is I'm going to take this guy and I'm going to move it to point D while keeping the same temperature, Tc. Remember, the temperature is lower now. Okay, so from here to there is an isothermal shrinking. Okay, from here to there is an isothermal expansion. Once we reach point D, D goes back to point A, also in an adiabatic process. So basically, what's a Carnot cycle? It's made of 4 steps. These 2 steps are isothermal, and those 2 steps are adiabatic. Okay, so the system is in contact with the hot reservoir from A to B. It is in contact with the cold reservoir from here to there. It absorbs heat and loses heat there, and there is no heat exchange for these 2 steps. That is a Carnot cycle. Okay, so what I'm going to do is I'm going to calculate the efficiency of the Carnot cycle. If I can do that, I would have found the greatest possible efficiency for any engine running between these 2 temperatures. You see? Okay, what is the definition of efficiency? E? Well, it is equal to W over QH. Okay, I'm going to put an absolute sign just to make sure that I'm calculating only absolute values. So E is positive. W is the work done. Okay, W is the area of the enclosure here, which is not very easy to calculate directly. So what I'm going to do is I'm going to use the first law of thermodynamics to simplify the calculation of W. You know, going from A to B to C to D and go back to A, what is the total change in the internal energy of this ideal gas? Well, that's 0 because it came back to the same point, right? Okay, how much heat did it absorb? It absorbed heat here and lost some heat there. So the total amount of heat absorbed, Q net, is equal to heat absorbed minus heat lost. So QH minus QC. Okay, what does the gas do with that heat absorbed? This is the net heat absorbed, right? It uses that to do work, of course, because you must use, suppose you get 100 joules of heat as a net result per cycle. You must convert that 100 joules 100% to do work. Otherwise, if there's anything left, if you only use 98 joules, you got 2 joules left, and that's going to increase your internal energy by 2 joules, but you know that doesn't happen because it came back to the same spot with exactly the same initial value of internal energy. So this must be equal to W, all right? So W equals QH minus QC, and therefore we say E equals W over QH, and that is QH minus QC divided by QH. So isn't that just 1 minus QC over QH? Okay, that is how you calculate efficiency. That's true for any cycle, not just Carnot cycle. But the Carnot cycle is unique in a sense that when you calculate QC and QH, QH is the heat absorbed going from A to B. That is an isothermal process. So is from the process from C to D. For any isothermal process, okay, so from A to B, we have QH, right? So A to B. QH, the absolute value of QH, Let's see, we apply the first law of thermodynamics to this step only from A to B. It absorbed this much heat. Since the temperature does not change, nor does the internal energy of the gas, right? So you don't have an internal energy change, which means whatever heat absorbed, you must convert that 100% to do work, WAB. That must be the work done by the gas. Alright? And do we know what that is? Yes, we do. This is we did this calculation before in the previous chapter. The work done by an ideal gas when it undergoes an isothermal process, PdV. You can do this calculation very easily. P using PV equals nRT, and remember T is a constant. You do this calculation, it's as a review. You will find the result to be equal to nRT times the natural log of V final over V initial, okay, which is VB over VA. And of course, this temperature is a temperature going from here to there is a T hot. Alright? That is the work done by, that is the heat absorbed going from point A to point B. It's equal to that. And since VB is greater than VA, it's a positive number. Meanwhile, let's look at the energy, let's look at the heat absorbed going from C to D. The answer is analogous, right? This is the heat lost by the gas going from point C to point D, Q cold. It is equal to the work done, the absolute value of the work done by the gas or on the gas, whatever, its absolute value from C to D. And then its formula is the same, nRT, C, this times T cold, log of VD over VC. Now let's be very careful here. VD is less than VC. All right, let's put this diagram back here. VD is right here, VC right there. So VD over VC is less than 1. The natural log is negative, but the whole thing has an absolute value. So when I take this absolute value away, I must reverse VC and VD. So it should be log of VC over VD if I want to stay positive. Okay, so this is nRTC log of VC over VD. So therefore, I found an expression. Okay, I found an expression for the efficiency of the Carnot cycle. E Carnot equals 1 minus QC over QH absolute value. And that equals 1 minus, I'm plugging in these results for QC and QH. Okay, QC is right here. nRTC log of VC over VD divided by nRTH log of VB over VA. Alright, now we can of course cross out NR here, but there is something about these natural logs that I don't like. What is it I don't like? Well, remember, the second law is a very general law, and it guarantees that any reversible engine operating between the same two temperatures, T cold and T hot, must have the same efficiency. There is no mention about what kind of reversible engine it is. Does it use gas expansion to do work? Does it use electricity? I don't care. Okay, any heat engine. But here we have something very specific about the nature of this operation. That is, we actually use ideal gas to do a Carnot cycle. You know, it expands to VC and then to VD and then go back to VB and to VA. Right? I mean, what if this thing does not even use expansion of ideal gas to do work? What if you use something totally different? Right? You don't have these quantities at all. So what did that tell you? This quantity is too specific about what kind of process I use to achieve the work done. And it violates the generality of the efficiency of any reversible engine operating between these two temperatures, TC and TH. In other words, I like the fact that TC is here and TH is here, but I don't like the fact that you have these two natural log functions. Okay, so what do we hope? We hope that we just get in a constant here. Okay, this thing in this red box really is just a constant, a number. Okay, now what do you think that number should be then? Well, let's see here. It's 1 minus TC times TH, and then times this number, right? Times this number, whatever it is. What do you think that number should be? I can argue that this number should be equal to 1? Okay, let's see why this number should be equal to 1. First of all, the efficiency is less than 100%, and therefore, whatever that number is, it's got to be positive, okay? It cannot have 0 or negative values. Otherwise, the efficiency would be greater than 1. You violate the first law of thermodynamics. Okay, so it's some positive number. But why do you think that number should be equal to 1? Well, let's say it's not equal to 1, okay? Let's say equal to 2, right? Just arbitrarily, it's equal to 2. If it's equal to 2, is that possible? Well, let's see now. What that means is that, okay, I'm going to put a question mark here. 1 minus 2 Tc over Th. You know what that means? That means is that whenever the cold temperature is half as much as hot temperature, in other words, when Tc equals half of Th, in other words, 2 Tc over Th equals 0, what do you think the efficiency is equal to? 0, because it's 1 minus 1, right? Now, isn't that strange? What that means is that, suppose, the cold temperature is 100 Kelvin, and this guy's 200 Kelvin, the engine all of a sudden has 0 efficiency. Okay? And worse yet, what if this guy is 200 Kelvin, and yet this T cold is 150 Kelvin? You get efficiency that's less than 0. That's even worse. How do you get efficiency that is less than 0? Right? The worst thing you can do is to make efficiency 0. Right? So that number 2 here doesn't make any sense, does it? In fact, you can argue for any other number. It doesn't make any sense, except for the number 1. So this really is just equal to 1. If it's 1, that's perfect. What that means is that, when Tc equals Th, okay, there is no temperature difference between these two reservoirs, and then the engine, it becomes useless. Because the reason why the engine works is because you extract heat from high temperatures, you dump part of the low temperatures, whatever left you do work. But when these two guys are the same temperature, you have lost this, potential difference, if you will. Okay, so the engine becomes useless. It also tells you that the only way to make the efficiency 100% is to make the cold temperature really, really, really cold. Now we know common sense tells us that in order to improve the efficiency of the heat engine, we want the hot temperature to be very hot, the cold temperature to be very cold, right? But unless the cold temperature is as cold as possible, which is 0 degree Kelvin, you're not going to get 100% efficiency. Okay? Of course, you don't quite get 0 Kelvin, therefore efficiency is always less than 100%. If it were equal to 100%, that would have violated the Kelvin-Planck statement. Okay? So it really makes sense to see that this thing in the red box be equal to 1. Of course, so far this is only an argument. We didn't quite show explicitly that this number equals 1. How do I show this number equals 1? Actually, all I have to show is that Vc over Vd equals Vb over Va, right? So the question is that true?